Hi, junior biochemists. Welcome to Module 2A. We're still in Chapter 2, still doing biochemistry, but this is Biochemistry Part B2. And as usual, we shall ask the question, where is God on this periodic table of elements? Shown: carbon, hydrogen, oxygen, nitrogen. And do you remember the two additional parts of CHON that some textbooks add? If you said phosphorus and sulfur, you're right. Okay, so last time we talked about organic and inorganic compounds. We said that generally, if you are an inorganic compound, you do not have carbon in you. A little more definition on salts. Salts contain cations. Remember, those are positive ions. They contain cations other than hydrogen cations, and they contain anions other than, remember this functional group? The hydroxyl functional group, or hydroxide ion in this case, because it has a negative charge. Salts will easily dissociate into ions in the presence of water. Examples: sodium chloride, table salt. Salts are vital. That means life-giving to many of our body functions. So for example, sodium and potassium ions are essential for nerve impulses. And we'll learn all about that when we do action potentials. But some salts, so this is just probably a photograph of some lab cabinet with all these salts in them. So for example, here's a K and an OH, so this would be potassium hydroxide. This is a salt. Here's some potassium bromide, potassium chloride, sodium chloride, so this is table salt. There's our old buddy table salt. But you could also be sodium hydroxide. But anyway, these are all examples of salts. And salts are important in your body. Salts are ionic compounds. So, for example, positive sodium and a negative chloride ion form an ionic bond. They'll dissociate in water, so they'll break apart when they're in water. And that means you'll have free sodium, positive sodium, and free negative chloride ions in water. That would be an electrolyte that can conduct an electrical current. You need to have your ions balanced for homeostasis, so that means you need to, drink your electrolyte solutions in the heat. And then some common salts in the body, we talked about that. Sodium chloride, calcium carbonate, potassium chloride, and then the calcium phosphates are important in bone. So here's a cartoon. It shows electrolytes, some common electrolytes that we get in the food and the stuff that we drink: sodium, bicarbonate ion, calcium ion, magnesium ion, potassium ion. And then here's some delicious electrolyte drinks, which probably costs like $5 for this bottle, and you can pretty much make your own electrolytes. So, a salt. If you are a charged particle, you're generally called a salt. So all salts are electrolytes, and electrolytes are ions like positive sodium and negative chloride that will conduct an electrical current. Get it? Electric current, electrolytes. Okay, now we're going to talk about acids and bases. So if you are an acid, you could be an organic acid or you could be an inorganic acid. Whether you're organic or inorganic, you will release hydrogen ions, free hydrogen ions, into water when you dissolve. And here's some interesting acids. Nitric oxide. Carbonic acid is really important physiologically and in terms of acid-base balance in your body. So we'll talk a lot about carbonic acid, especially in 202. Hydrochloric acid, you guys probably know that's your stomach acid. Sulfuric acid is really dangerous. Acetic acid is vinegar. Citric acid you find in citrus fruits. Now, why did I put this cartoon up? So this shows hydrogen from the periodic table of elements. Its atomic number is 1. That means it has 1 proton. And then that also means if it has 1 positive proton, so if it's got 1 positive charge, then that means it has to have 1 electron, 1 negative charge to balance. So 1 positive balances with 1 negative, and that makes the hydrogen atom electrically neutral. But if you are a hydrogen cation, that means you've lost your 1 negative electron. That means you look like this, hydrogen cation, and really all you are is a proton. So sometimes they call free hydrogen ions protons. If you're an acid, you can be strong, like hydrochloric acid. If you're a strong acid, that means you completely dissociate in water into free hydrogen ion and chloride ion. They liberate all their free, if you're a strong acid, you liberate all your free hydrogen ions. And then if you're a weak acid, you ionize incompletely. So if you are a weak acid, you only liberate some of your free hydrogen ions. Here's examples of some acids, common acids that you guys know: vinegar, lemon juice. Soft drink is acidic. Battery acid, yeah, it's acidic. Stomach acid, yeah. Apple juice and black tea are both acidic as well. Okay, those are some facts about acids. Now what about bases? Most bases are inorganic. Here's a photograph of some common household bases. So for example, sodium hydroxide you find in drain cleaner, and its formula is NaOH. So here's the sodium, here's the hydroxyl ion. Together they're called sodium hydroxide. Potassium hydroxide is KOH. Calcium hydroxide is calcium plus 2 hydroxides. And here's the ions that make it. So calcium usually comes as a +2, and if you have 2 negative charges, so you have positive 2 plus 2, and then you have 2, so this number that goes in the front of the hydroxyl ion means there's 2 negative charges, 2 positive and 2 negative charges. It balances out. It's electrically neutral. Calcium hydroxide is electrically neutral. Same for this potassium hydroxide. Potassium has 1 positive, hydroxide has 1 negative. They balance each other out. They're electrically neutral. And then aqueous ammonia. So here's some ammonia cleaner. It says ammonia here. Ammonia is NH3. Aqueous ammonia is NH3. And then here's the ions that make up ammonia. So bases technically release hydroxyl ions when they're dissolved in water. So acids, remember, release free hydrogen ion. Bases release hydroxyl ions when dissolved in water. Bases are also proton acceptors. So if you're an acid and you release your free hydrogen, if there's a base nearby, it can accept that free hydrogen. Acids and bases can work together. So for example, here's sodium hydroxide. Remember, you find that in drain cleaner. Reaction goes to the right, release free sodium ion and free hydroxyl ion. You are a base. If you are a strong base, remember there are strong and weak acids. If you are a strong base, you will dissociate, and your hydroxyl ion will seek a free hydrogen ion to make water, H2O. So here's 1 hydrogen. Here's another hydrogen. That's 2 of the hydrogens, and then one oxygen will make a water molecule. So important inorganic compound reactions. There's a neutralization reaction. This is a type of exchange reaction in which acids and bases react to form a water and a salt. So here's hydrochloric acid. Here's the base, sodium hydroxide. They do an exchange reaction. So this OH from the base one of those, that one oxygen goes here, and one of the hydrogen from the hydroxide ion group goes there, and then from the acid, the H in the HCl is the other hydrogen. So, and then the sodium and the chloride from the acid go over here to make salt. So this is a neutralization reaction. The type of reaction is an exchange reaction. So you just exchange your atoms or your functional groups, and if you are an acid and base, you're put together, you make a water and a salt. Here's the pH scale. Everybody's heard of pH. You probably know, or you may know, that a low pH, like 1, means you're very acidic. A high pH, like 14, means you're very basic. And in this cartoon, it kind of shows a basic solution. So here's a beaker. You've got your free hydroxy ion. Then you have a whole bunch of hydroxide ion. That means you're a base. If you're an acidic solution, you have a whole bunch of free hydrogen ion, H+. That means you're an acid. If you have equal number of hydroxide ion and free hydrogen ion, then you are a neutral solution. And then here's some examples of acids and bases. And it's obvious, right, that lemon juice is acidic. Did you know that wine was acidic and coffee? Milk is a little bit acidic. Blood is a little basic chemically with a pH of 7.4. Eggs are basic. We said that ammonia was basic, so is bleach. Oven cleaner, lye, sodium hydroxide is also basic. So the pH scale, what does it do? It measures the relative concentration of free hydrogen ions relative to the hydroxide ion in the solution. So for example, in the neutral solution over here, the free hydrogen ion relative to the free hydroxide ion is the same. It's equal. 1-to-1 ratio. pH scale technically is based on the number of free protons or free hydrogen ions in a solution. So this is where it gets real tricky, and you just have to memorize this. When the concentration of free hydrogen ion goes up, the pH goes down. It's weird, huh? But that's the way it is, because it's a negative log scale. So that means when you have if you come over here to the acidic solution, free hydrogen ion has gone up relative to the hydroxide ion. So that means free hydrogen ion is high. Free hydrogen ion is high. That means the pH is low. So pH down here is like 1 through 6.999. Free hydrogen ion is expressed in moles per liter, or molarity. We won't get into that too much. Each successive change on the pH scale, so successive change, that means 1. What succeeds 1? 2. What succeeds 2? 3. So each successive change, so for example, from 1 to 2, or from 2 to 3, represents a 10-fold change in the concentration of free hydrogen ion, because it's a negative logarithmic scale. That's why. So it's log scale. You jump by 10. So from 1 to 2 is not merely one jump. 1 to 2 is 10 jumps. So if you go from a pH of 1 to a pH of 2, you decrease your free hydrogen ion 10-fold. If you go from a pH of 1 to a pH of 3, you decrease your free hydrogen ion 100-fold. If you go from a pH of 1 to a pH of 4, you decrease your free hydrogen ion by concentration of 1,000-fold. So get it? So from 1 to 2 is 10. From 1 to 3 is 100. From 1 to 4 is 1,000. From 1 to 5 is 10,000. From 1 to 6 is 100,000. From 1 to 7 is 1,000,000. That's a log scale. So let's look at this question. Compared to an acidic solution at pH 5, right there, basic solution at pH 8 has, well, first of all, we know it's got less hydrogen ions. So anything that says more hydrogen ions is wrong. So we cross out A. If you go from pH 5 to pH 8, so from 5 to 6 is 10, 6 to 7 is 100, 7 to 8 is 1,000. And you've got less free hydrogen ion if you're basic, so the answer is B. So be able to answer test questions. If you have a pH of 7, that's neutral. The number of free hydrogen ions exactly equals the number of free hydroxyl ions. We said this below pH 7, you're acidic. Above pH 7, you're basic. If you are a buffer, you are a chemical that can regulate pH changes. So, for example, there are buffers in your blood that if you drank 10 gallons of lemon juice, well, maybe you wouldn't do that, but if you drank a bunch of lemon juice, there's buffers in your blood that will not let your blood get too acidic. So a buffer will resist a large fluctuation in pH. That would happen if you drank a whole bunch of lemon juice. And if your blood fluctuates in pH, that could damage your living tissue. Bicarbonate buffer system. This is the most important buffer system in your body in terms of physiology, in terms of 2O2. And here it is. So here's the bicarbonate buffer system. So here's the bicarbonate ion that it's named for, the bicarbonate buffer system. And you can see there's an arrow going to your kidneys, to and from your kidneys. That means that your kidneys can either hold on to bicarbonate ion or your kidneys can excrete bicarbonate ion, depending what your body needs. And you come over here, you guys know you breathe out CO2, and so it shows here from the lungs. So you breathe in fresh oxygen. You also breathe in a little CO2 as well, but you can get more detailed out when you take 2O2. But so you breathe in fresh oxygen, you breathe out CO2. But you've got CO2 in your blood, and you've got water in your blood, and you've got carbonic acid in your blood, you have free hydrogen ion in your blood, you have bicarbonate ion in your blood. And this whole thing is called the bicarbonate buffer system. And you can see it's got those dual arrows, so the reaction can go either way. And you use this bicarbonate buffer system because the pH of your body fluids must remain constant to maintain homeostasis or you get sick. So the pH, if you remember what I just told you, the pH is a measure of the free hydrogen ion concentration. So if you get a whole bunch of free hydrogen ion in your blood, that means your blood will become acidic. That means that you could die. It also means your pH is very low. Remember, high free hydrogen ion, low pH, you're acidic. So this system, bicarbonate buffer system, can control this free hydrogen ion. So for example, if for some reason you accumulate a lot of free hydrogen in your blood, if the reaction goes this way to the left, that free hydrogen ion will be soaked up by bicarbonate ion. You'll form carbonic acid. Carbonic acid will dissociate into water and CO2, and you'll breathe out the CO2. That's how you can regulate your free hydrogen ion concentration, which determines the pH. So which of the following acts as a pH buffer in blood? Carbonic acid, this guy, bicarbonate ion. There is no carbonate ion in this cartoon. And the hydroxide ion, there is no hydroxide ion in this cartoon. So the answer is bicarbonate ion. Well, technically it's bicarbonate ion, but it could also be carbonic acid. So sometimes, depends on the book, they'll call it the carbonic acid bicarb buffer system. Other books will call it the bicarbonate buffer system.